Welcome to video lecture F8. This one is on diagonalization of real symmetric matrices. I'll be your leader, Tom Roby, and here are the outline and objectives. We're going to combine the geometric work we've done recently on orthogonality and projections with the algebraic work that we did earlier on eigenvalues, eigenvectors, and the change of basis to analyze the following fundamental result, which is that every symmetric matrix, every matrix which is equal to its own transpose, is orthogonally diagonalizable. So you can write it as PDP inverse, where in fact P is an orthogonal matrix. Now this is pretty exciting because we know that if generically, if you just take any matrix in R n by n matrix, it may not even be diagonalizable, much less orthogonally diagonalizable. So to have a case situation where we know that we always get diagonalizability is really quite nice. And finally, I'll give an example of how to compute this in practice. So first, let's recall a few definitions and make sure we're straight on all the terminology. So what's a symmetric matrix? Well, that means that A equals A transpose. So which of these matrices are symmetric? This one, let's see. In order to be symmetric, if I took the transpose of 1, 2, 3, 1, I would get 1, 3, 2, 1. And those aren't the same, right? So these off-diagonal entries, 2 and 3, that are symmetrically placed have to be equal to each other. So I can make it symmetric by making this a 2 or this entry a 3. How about B? Well, B, you see, the diagonal doesn't matter, right? These don't have to be the same, but the off-diagonal entries do. So this matrix is its own transpose, so that one is symmetric. And finally, if you look at this one, you can see, well, it's almost symmetric, except that, again, the 0 and the 3 need to be the same. So I either need to make this one a 3 or this one a 0. OK. So that's what symmetric means. And remember that a matrix is orthogonal if its transpose is the same as its inverse. In other words, if you multiply it by the matrix by its transpose, you get the identity matrix. And that should make some sense, right? Because a matrix that's orthogonal is one whose columns are orthonormal, meaning that the inner product of any two of them is usually 0 if they're different and 1 if they're the same. But that just corresponds, if you take U transpose times U, you're just multiplying the ith row of U. You're just taking two columns, and one of them's become the row when you take the transpose, and you're just saying that the inner product of those column vectors is equal to 0 if they're different and 1 if they're the same, and that's why you get the identity matrix that looks like this. Okay. So is this matrix orthogonal? Sure. Every column has unit length, and if you look at the inner products pairwise, you get 0 all the time. This is the nicest possible basis, the standard one. How about this one? Well, if you look for orthogonality, you find that if you take the inner product of the first and second column, that's orthogonal. First and third, you get 0. Second and third, you get 0. So the columns are orthogonal. But that's not enough, remember, for it to be an orthogonal matrix because we don't have orthonormality. So in order to make this an orthonormal matrix, we would have to replace it with by normalizing all the entries. So what I would do is say m prime is equal to 1 over the square root of 2, 0, 1 over the square root of 2, 0, 1, 0, and then 1 over the square root of 2, 0, negative 1 over the square root of 2. And that would be a matrix that when I multiply it by its transpose, I get the identity. OK, now if you look at P, this isn't a good example of a matrix where all the columns are normalized already, right? Because this 1/5 means I'm dividing. This is 3/5, negative 4/5. OK, so I've basically just pulled the factor of 5 out in front because the norm of each of the vectors inside this matrix is 5. And so if I divide by 5, they all have norm 1. So the only question is, are they orthogonal? And you check, OK, well, the first and second are orthogonal. First and third, oh, whoops, they're not, right? Because 3 times 3 is 9. And so you end up with the inner product of the first two is going to be, well, 9 divided by 5 squared. So in any case, it's not, this matrix is not orthogonal. And to make it so, you'd have to fool around with it a little bit. So now remember what we did about diagonalizability. It's only something that applies to square matrix. And a square matrix is diagonal. The definition is if it's similar to a diagonal matrix, which means that it can be written as P d P inverse, where D is diagonal and P is invertible. But we showed that that was equivalent to A having n linearly independent eigenvectors. And in fact, the eigenvectors are just the columns of this matrix. Since they're linearly independent and there are n of them, that means that these form a basis. And so the columns form a basis for r to the n, which means that this is an invertible matrix. And then the diagonal entries are the corresponding eigenvalues. And they have to correspond. And so lambda 1 corresponds to v1, lambda 2 corresponds to lambda 1 corresponds to v1, lambda 2 corresponds to v2, and so on. Lambda n corresponds to vn. You can have repeats here in the eigenvalues. And so now the precise definition of something being orthogonally diagonalizable is that I can write it as PDP inverse for some orthogonal matrix P. But if it's true, remember that P inverse is just another name for P transpose, so I can also write it as PDP transpose. Okay, and so that, for one thing, it makes it easier. You don't have to compute an inverse. It's easy to write down the transpose, not so easy to write down the inverse of a large matrix. Okay, so here's something that shows you that orthogonal diagonalizability is not something that you would expect every matrix to have, right? I mean, ordinary matrix, we don't even expect it to be diagonalizable at all. But if it's symmetric, it will be diagonalizable. And if it's orthogonally diagonalizable, it actually has to be symmetric. Okay? And the proof of this is one line, right? Because if A is equal to P transpose now, right? Because P transpose equals P inverse, since P is an orthogonal matrix, then what happens when I take the transpose of that? Well, to take the transpose of a product of things, I just reverse the order and take the transpose of each piece. Okay, so the transpose of this thing becomes P transpose transpose, so I get P transpose transpose, D transpose P transpose. Now, if you transpose something twice, you get back where you started. If you transpose a diagonal matrix, it doesn't change it, because there's no off-diagonal entries to worry about. And P transpose is just what it is, and that's just the same thing as P transpose, which is, of course, A. Okay? So you can only orthogonally diagonalize a symmetric matrix. That's the easy direction. The harder direction is that, in fact, the converse is also true. So if it's a symmetric matrix with real entries, then it can always be orthogonally diagonalized. Now here's one more lemma to discuss in this context. If A is a real symmetric matrix, then any two eigenvectors from different eigenspaces will be orthogonal. Okay? So you give me one eigenvector that corresponds to 3, another eigenvector that corresponds to 2. If I take the dot product of those two vectors, I have to get 0. Right, so why is something like this true? Well, here's the start of the proof, and I'll finish it off by hand. Suppose that I've got one vector that's an eigenvector corresponding to lambda, and w corresponds to mu, and lambda and mu are different. So they correspond to different eigenvalues. Then what I want to claim is that if I look at lambda of v dot times v dot w, that'll be the same as mu times v dot w. But if lambda and mu are different, the only way you can have 2 times something is equal to 3 times something is if that something is 0. Okay, so that forces v dot w equals 0, which means that v and w are orthogonal. All right, so let's see how that proof goes. So what do you get? You get that, so if I look at lambda of v dot w, well, that's lambda v dotted with w, right? Now lambda v, since this is an eigenvalue for A, that's equal to AV dot w. And now AV is just, remember, we're taking the dot product, is just the same thing as taking the transpose of this vector times that other vector. Okay, so that's equal to AV transpose dot w. Not dot, so sorry, no dot now, right? So that's the point. It's just equal. This is just multiplication of a column vector, of a row vector times a column vector now. Okay, so I take AV transpose times W, and that, by the property of transpose that we just used, is V transpose A transpose W. All right, but now I can reassociate this as V transpose A transpose W. Okay, and so now you really can't stop me, right? A transpose W, I know that this is a symmetric matrix, right? That's one of my hypotheses. So A transpose equals A. So I use that, and I get that this is V transpose AW, and that's equal to V transpose AW. Since W is an eigenvalue for mu, this is V transpose times mu W. Mu is a scalar, pulls out, I get mu times V transpose times W. And now V transpose times W is just V dot W. Okay, so this is equal to mu times V dot W. Okay, so a simple chain of equality shows me that lambda times V dot W is equal to mu times V dot W. And the only thing, crucial place where I use the hypothesis is where I replaced A transpose W with just AW. Okay, so I really needed the symmetry there. Okay, so that's a really nice lemma. And here's the full-blown spectral theorem. This is one of the great theorems of linear algebra. It's the spectral theorem. There are different kinds of spectral theorem. The reason it's called spectral is because spectrum is one word that gets used for the set of, or the multiset of eigenvalues of the matrix. So the lambda 1 through lambda n, that collection is called the spectrum. And so this is the spectral theorem, and I won't say more about why it's called that. But if I have a symmetric matrix, a real symmetric matrix, then it has to have n real eigenvalues, counting multiplicities. We know that for a general matrix, you might not have as many, you might not have them all be real eigenvalues. You might have some complex eigenvalues. Right? And just a quick example of that is, remember, if you take the matrix that, say, rotates by pi over 2, then it takes 1, 0 to 0, 1, and it takes 0, 1 to negative 1, 0. Right? So this is a rotation matrix. I'll just call it R. Then what's its characteristic polynomial? Then the determinant of R minus lambda I is the determinant of minus lambda minus 1, 1 minus lambda, and that's equal to lambda squared plus 1, right? And so there are any eigenvalue has to be a root of this polynomial, but there are no real roots. The roots of this are plus or minus I. So this is an example of a matrix whose entries are all real, but I need to have complex eigenvalues in order to talk about all of its eigenvalues. And what this theorem is saying is that if this matrix is not symmetric, as you can see, but if I had a symmetric matrix, I wouldn't be able to do this. I would have to get a polynomial that would factor into linear factors with real numbers. Okay, so now, you have all real eigenvalues, and the dimension of all the eigenspaces is as big as it can be, as big as you want it to be in order to be diagonalizable. So you look at the dimension of that eigenspace corresponding to lambda, and you end up getting that it's the multiplicity of lambda as a root of the characteristic polynomial. And now finally, if lambda and mu are different in spec of A, right? So that's the spectrum, the set of eigenvalues, then E lambda is perpendicular to E mu. In other words, every vector in E lambda is perpendicular to every vector in E mu, so their dot products are 0. But that's exactly what this lemma said. So this lemma is basically the proof of 3. And finally, under all these conditions, you get that A is orthogonally diagonalizable. Okay, so because all of these eigenspaces have the right dimension, they're all full dimension as opposed to being smaller, then we end up getting diagonalizability, and then we can convert that to orthogonal diagonalizability using Gram-Schmidt. Okay, so let's do an example here. Okay, so let's look at a full-blown example of orthogonal diagonalization. So what's the point? We've got a symmetric matrix, real entries, and the first thing you should notice when you look at a matrix, you might say to yourself, are there any obvious eigenvalue-eigenvector pairs? And one thing you notice is there's this nice kind of circular symmetry to this matrix. And in particular, if you take the sum of all the rows, you always get the same thing because it's just the same entries kind of permuted. So the sum of each row sum of this matrix is equal to 6. And what that means is that if you take this matrix and you multiply it by So let's just show this, right? If you take 4, 1, 1, 1, 4, 1, 1, 1, 4, and you multiply it by the vector 1, 1, 1, that's actually just computing all the row sums of this matrix, right? So what do you get? 4 plus 1 plus 1 is 6. 1 plus 4 plus 1 is 6. 1 plus 1 plus 4 is 6. Okay, and that's 6 times 1, 1, 1. So what that means is that this is an eigenvector corresponding to the eigenvalue 6. Okay, so sorry, I should have asked that question first. What's an obvious eigenvalue-eigenvector pair? And now you see the answer to that. So, of course, if you hadn't realized that, it's no problem. It just might be a little bit harder for you to factor this cubic polynomial. Okay, but if you know that one of the eigenvalues is 6, then you know that 6 is a factor of this. You can also, if you're guessing that they're integers, then you could look for factors of 54 and try a few before you found one that worked. But it turns out that the other two, the other eigenvalue is 3 of multiplicity 2, okay, because I have a lambda minus 3 squared. Right. Now, in practice, the software packages that you're using have better numerical methods for figuring out, computing the eigenvectors and eigenvalues of any kind of matrix. But in order to illustrate the ideas, it's useful to know how to handle it for the hand techniques that we're using here. OK, so then what do? Well, our usual algorithm for figuring out how to deal with to figure out what the eigenvectors are is we look at the eigenspaces, right? So for example, we've already figured out that E6 is going to be the span of the vector 1, 1, 1. And then E3 is, of course, the null space of this matrix A minus 3 times the identity matrix. And that turns out to be the span of 2 vectors, which is good because this had multiplicity 2. So we want to get 2 eigenvectors so that we can do this decomposition. And so you end up getting A equals PDP inverse, not as an orthogonal decomposition, but just as a regular decomposition, diagonalization of this matrix. So we factored it in this way. This is the inverse of that matrix, as you can easily check. And so E3, and this is going to be the span of these second 2 column vectors, 1, 0, negative 1, and 0, 1, negative 1. OK, oops, it's going off the screen. Oh, well. But you can see them here. It's the same vectors that are here. OK, so what's my point? Are the columns of P orthogonal? Well, notice that if I take this column and I dot it with the second column, I do get 0. And if I dot it with the third column, I get 0. But we actually knew that already, right? Because this is an eigenvector corresponding to 6. And these are eigenvectors corresponding to 3. And this is a symmetric matrix. So that means that these guys actually, every vector corresponding to 6 has to be orthogonal to every vector corresponding to 3, which each of these are. But if you look at the vectors corresponding to 3 and you take their inner product with each other, you get 1. So they're not orthogonal to each other. So how do we fix that? If we've got a basis for a space like E3, the eigenspace corresponding to 3, and it's not orthogonal, well, we fix it using Gram-Schmidt. Okay, so now to use Gram-Schmidt, so you check that the columns of P are not orthogonal. Now what should we do? Apply Gram-Schmidt to the columns of P as needed. So what do? So this one is already orthogonal to everything, so we don't need to worry about it. It's just these two that we need to deal with. And so I'll let my new vector, so V2 will just continue to be 1, 0, negative 1. And V3 will be, well, it'll be V2, 1, 0, negative 1, minus the inner product of these two guys, which was 1, divided by the norm of this guy, which is 2, times, so V3 is going to be the third vector, 0, 1, minus 1, right? Minus when I project it onto the second vector. Okay, so the second vector is 1, 0, minus 1. And when you compute that out, what do you get? You get 0 minus a half is negative 1/2. And 1 minus a half times 0 is still 0. And minus 1 minus 2 minus signs plus a half is negative 1/2. Okay? So I'm going to replace this third vector with this vector. And in fact, I might as well, I mean, really, I can think of this as being, I can rescale it however I want. So first I'm going to rescale it as minus 1, 0, minus 1, where it's really easy to see that, that these two vectors are orthogonal. And now, of course, I'm going to, oops, I did something wrong. What did I do wrong? Ah, right, this should have been 1 minus 0. So that was a carefully planned mistake to see if you were paying attention. So this should be a 1, right? Because I get 1 minus a half times 0. OK, so now when I rescale it, this is actually minus 1, 2 minus 1. And now let's double check. When I take minus 1, 2 minus 1, and I take the inner product, then I get minus 1, 0, plus 1, so they dot to 0. OK, but really what I'm going to do with this is I want to divide it by the square root of 6. So this is really going to be minus 1 over the square root of 6, 2 over the square root of 6, minus 1 over the square root of 6, because I want to divide it by its norm to make sure it's normal. It is norm 1. And so then what happens? So now I claim that A equals Q dQ inverse, which is the same as Q dQ transpose, where Q is this matrix where I've Gram-Schmidted the third column to make it minus 1, 2, minus 1, and then divided it by its norm to get divided by every entry by the square root of 6. Similarly, for the first and second columns, I divide by their norm, and I get 1's over the square root of 3 here, and 1 over the square root of 2, and negative 1 over the square root of 2 in this one. Okay? And so that's the factorization. If you take this matrix, and you can write it as this Q times the same diagonal matrix, 6, 3, 3 on the diagonal, times the transpose of this matrix. You don't have to actually do anything fancy to take the inverse. And if you like, you can check that this is actually an orthogonal matrix. How would you do that? Well, you could just take this matrix and multiply it by its transpose, right? So if I multiply it by its transpose, then I've got 1 over what I had going down is now what's going across. I've got 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. And now going down the second column, I've got 1 over the square root of 2, 0 minus 1 over the square root of 2. And then going down the third column, that becomes my new third row, I've got minus 1 over the square root of 6, 2 over the square root of 6, minus 1 over the square root of 6. Yeah, that's right. Okay, and so now let's multiply these guys. What do I get? If I take this product, then I get a third plus 1 over the square root of 6. See, did I do this right? I should be taking this row dotted with so I get over the square root of 6. Ah, right. So I end up with a third plus a half plus a sixth, which gives me 1. Right? So this entry becomes 1. If I take this guy dotted with this guy, I get a third plus 0 minus 2 over the square root of minus 2 sixths, which is a third. So I get 0. Okay? And so if you check all those entries, you'll find that you get this. Okay? So that's it for video lecture F8. Thank you very much for your kind attention.